Rotating electrical machinery is a part of much military equipment. Whether it is a simple blower or a complicated electronic device in a missile, they all depend on the proper functioning of rotating electrical equipment. Two types of motors and generators are commonly in use: alternating current or AC and direct current or DC motors and generators. This film will show the principles governing the operation of DC motors and generators. Basic to the understanding of DC motors and generators is the simple generation of an electromotive force, an EMF. Mechanical energy, the moving of a wire or conductor across a magnetic field by hand in this instance, produces electrical energy. The magnetic field is composed of lines of force. As the conductor cuts these lines, an electromotive force or EMF is generated in the conductor. Moving the conductor down through the field makes the needle of a voltmeter deflect one way, which means the EMF has one direction. Moving the conductor up through the field produces the opposite deflection of the needle. The EMF has now changed direction. Moving the conductor back and forth with the field does not make the needle of the voltmeter deflect. There is no EMF because the conductor is not cutting the field. To illustrate the direction of current flow, the conventional symbols will be used. Current flowing in a conductor away from us is represented by a cross, toward us by a dot. However, moving a conductor in and out of the field in this straight reciprocal fashion is awkward and impractical. A simple generator of EMF can also be made by rotating a single turn coil within a stationary magnetic field of two magnets with opposite polarity. The loop now, in effect, becomes two conductors because both the top and bottom sections cut magnetic lines during rotation. Since they cut lines of force of opposite directions as they rotate, EMFs of opposite polarity will be generated in the conductors. In order to have current flow in this circuit, polarities of the two conductors must be opposite. The amount of EMF generated at any instant is determined by three factors: the strength of the magnetic field, that is, the number of lines of force, the length of the conductor cutting the lines of force, and the velocity with which the conductor is turning. We can determine the amount of instantaneous EMF by a simple formula. The instantaneous EMF E equals B, the strength of the field, times L, the length of the conductor cutting lines of force, times V, the velocity of the conductor. An increase in the number of lines of force or the strength of the field increases the instantaneous EMF in the conductor. Increases in the length of the conductor cutting lines also increases the EMF. And finally, the greater the velocity of the conductor, the greater the EMF. This formula assumes conductor motion in a straight line, that is to say, cutting the same number of lines for each increment of its motion. But the conductor in an actual machine is not moving in a straight line, but rotating. When the conductor moves in a rotary path, the number of lines cut varies depending on the position of the conductor. At the top of the field, for instance, no lines are being cut and no EMF is generated. As the conductor keeps turning, the number of lines cut increases, so that at a quarter turn or 90 degrees, the maximum number is being cut and maximum EMF is generated. Again, at 180 degrees, no lines are cut, no EMF. We reach a maximum again at 270 degrees, and finally, again at 360 degrees, no lines are cut. The conductor has rotated 360 mechanical degrees, which correspond in this instance to 360 electrical degrees. Therefore, when the conductor moves in a rotary path, another factor is added to the original formula for the determination of instantaneous EMF. The formula that now applies is instantaneous EMF equals field strength times the length of the conductor times velocity multiplied by sine theta. Theta is the angle formed by the flux line and the motion of the conductor. The number of lines cut and the amount of EMF generated is proportional to the sine of the angle formed by the magnetic lines with the conductor motion. A graph of EMF versus conductor position during one revolution will be a sine wave representing alternating current, or AC. All rotary generators produce AC internally. What you have seen so far is really the theory and operation of a basic AC generator, but our purpose was to explain the principles of operation of a DC generator. To get direct current, we will attach each end of the conductor to a segment of copper forming a commutator. Now our machine is a DC generator. The commutator rotates with the loop. Stationary contacts, carbon brushes, ride on the commutator segments. They provide a means of connecting a meter or any other load to the generator. The loop of a conductor, wound on a rotor, and the commutator are referred to as the armature. As the loop revolves and the EMF in the conductor reverses polarity, the connections to the load are also reversed and the current flow will maintain the same direction externally. Represented graphically, the output amplitude still varies. The DC is in the form of pulses. It is a pulsating direct current, or PDC. The pulsation from 0 to maximum, twice for each revolution of the loop, is called ripple. This ripple can be reduced by adding more loops and more commutator segments to the existing armature. 2 loops at right angles connected to 4 commutator segments provide 2 outputs instead of 1. These outputs are 90 degrees displaced or apart, which combine to smooth the DC output. However, even with 2 loops and 4 commutator segments, the rectified curve is still somewhat irregular. By adding magnets, we increase the number of fields cut by the armature. As we increase the number of loops and commutator segments, the variation between maximum and minimum value decreases. This, in effect, tends to flatten the DC output. Practical DC generator armatures have a great many loops wound on a rotor. The field is composed of many electromagnets. Together, these factors tend to create an almost pure DC output. An important problem in the design of generators is the prevention of sparking between the commutator and the brush assembly. The prevention of sparking depends on the position of the brushes. This line through points of zero generated EMF is called the neutral plane. Placing the brushes in this neutral plane reduces the tendency for sparking between brushes and commutator, because during the time a brush is touching both commutator segments, there is no difference in potential between these segments. Theoretically, no sparking should occur at the commutator brushes when they are placed in this position. But the current flowing in the armature loops or coils sets up a magnetic field of its own. This magnetic field interacts with the main magnetic field and distorts it. The distortion causes a shift in the neutral plane and sparking at the brushes. The effect is called armature reaction. Sparking may cause severe interference in nearby electronic equipment. There are two ways of maintaining the neutral plane in its correct position and thus avoiding sparking. It may be done by the adjustment of the brush position. The brushes are adjusted to lie in the adjusted neutral plane. The other way of maintaining the neutral plane is by adding interpoles to the generator field. These interpoles are small magnets placed between the poles of the main field magnets. The interpole fields oppose the fields created by armature reaction. The neutral plane is moved back toward the correct position. In addition, to further counteract armature reaction, windings called compensating windings are sometimes placed in the main pole faces. The current in these windings is armature current flowing in opposite direction to the current in the armature conductors. Magnetic fields in DC generators may be produced by electromagnets or permanent magnets. Permanent magnets are used in relatively small devices like a field telephone ringing generator. In larger generators, the field is created by electromagnets. The field winding used in this DC generator can be represented by a symbol. The symbol is that of an iron core inductor. Current to excite the field windings can be supplied from an external source. In that case, the generator is classified as separately excited. A small part of the generator's own output can also do the exciting. In that case, it will be a self-excited generator. Self-excited generators must be initially magnetized. The residual magnetism in the core of the field winding provides enough magnetism to begin generator action. The field coil winding may be connected in several ways. This is a series wound generator, which means the field coil is in series with the armature. Because of this series arrangement, it has poor voltage regulation. The reason for this can be demonstrated in the following manner. Additional load will cause more current to flow in the field coil. Increase in field strength increases voltage. Increase in voltage causes more current to flow. This continuing action stops only when the core is saturated. When the load is increased, the voltage will increase. When the load decreases, voltage will decrease. Voltage regulation in the series wound generator, therefore, is very poor. When instead of in series, the field winding is connected in parallel with the armature and the load, we have a shunt wound generator. Now the field current is independent of the load current. Therefore, an increase in armature current will not cause an increase in the voltage output. Voltage regulation here is greatly improved. In shunt wound generators, therefore, changing load causes relatively small change in voltage output. By changing the armature winding, a compound wound generator results, which combines the best features of both types, the series and the shunt wound generator. When windings are arranged so that magnetic fields oppose each other, it becomes in effect a series generator. This is used only where constant current is the prime requirement, such as in arc welding. By changing the magnetic polarity of one of the field windings aid one another. As a result, this compound wound generator has good voltage and fair current regulation. A graphic representation of generator output characteristics with terminal voltage plotted vertically and armature current horizontally would look something like this. As we have seen, in the output of the series wound generator, voltage regulation is very poor. In parallel or shunt wound generators, the voltage regulation is fairly good, but current regulation is poor. Compound wound generators offer a flat compounded output that is normally most desirable. It combines the good features of both the shunt and series wound generators and provides stable voltage output under changing loads. As we have seen in our analysis of the DC generator, its primary function is the conversion of mechanical energy to electrical energy. If we now reverse the procedure and connect an electrical power source to the generator, we have a DC motor instead of a DC generator. Motor action can be illustrated by attaching a power source to a conductor which is inside a magnetic field. The electric current creates polarity in the conductor. The south pole of the magnet attracts the north pole of the conductor and repels the south pole. The north pole of the magnet attracts the south pole of the conductor and repels the north pole. This creates movement depending on the direction of the steady magnetic field. The movement also depends on the direction of the current flow through the wire. By changing the polarity of the battery, the conductor now moves in the opposite direction. To see what really happens, let's go to a drawing again. Here, a conductor is suspended in a magnetic field. Current flow from a power source creates its own magnetic field in and around the conductor. This field around the conductor reacts with a main magnetic field to cause motion of the conductor either out of the field or into it. The arrow point indicates the direction of the current flow in the conductor. In this case, the flow is toward us. The field of the conductor has the same direction as the main field above the conductor and the opposite direction of the field below the conductor. These two magnetic forces added together distort the lines of the main field upward. The field above the conductor is thus made stronger and the field below the conductor is made weaker. So the conductor moves down. Conversely, when current flows in the opposite direction, that is to say, away from us, the field of the conductor opposes the main field above the conductor. This aids the main field below the conductor, distorting the lines down. The field below the conductor is thus made stronger, while the field above the conductor is made relatively weaker. This forces the conductor to move up. With this basic principle of motor action understood, we can now examine the DC motor. The basic DC motor, like the DC generator, consists of a pair of magnetic poles, an armature made up of a single turn loop, a commutator, and a brush assembly. As we have seen, a conductor in a magnetic field will move when a voltage is applied to it. With a voltage applied, and the magnetic field and current flow as shown, the right conductor will be pushed down, while the left one is pushed up. Since the forces on each conductor are now in exact balance, there will be no more motion. Adding another loop and two commutator segments ensures that at no time will balancing forces cancel each other out. With this setup, there will be motion at all times. As one commutator segment is moved away from the brushes, another now takes its place and the movement continues. The greater the number of loops in the armature, the smoother its motion. For this reason, rotors in practical DC motors have many loops. Since current in the rotor loops must reverse each half cycle, two commutator segments per loop are required. Here in the motor, as in the DC generator, there is a neutral plane. The interaction of the conductor fields on the main field causes this neutral plane to shift and sparking to occur when a load is added. Sparking in DC motors also produces burned commutators and interference in nearby electronic equipment. This sparking can be prevented in one of two ways. One is by the adjustment of the brush position. The brushes are moved until they lie in the adjusted neutral plane. In the motor, as in the generator, small interpoles between the poles of the main magnets are also used to eliminate the shift of the neutral plane. These interpole fields tend to oppose the fields created by armature reaction. The neutral plane is moved back toward its correct position. Also aiding are compensating windings, which carry armature current in the opposite direction to the current in the armature conductors. The neutral plane is thus maintained in its proper position. DC motors operate most efficiently when sparking is eliminated. We saw earlier that when a conductor is moved by mechanical energy in a magnetic field, an EMF is generated. This is generator action. In the DC motor, when rotation is desired, it is necessary to apply an EMF to the conductor. However, when used as a motor, an opposing EMF is also generated in the conductor. This is called the counter-electromotive force, or CEMF. By Lenz's law, the generated CEMF must oppose the applied EMF. The amount of CEMF depends on the speed of rotation. This is of practical importance in large motors. When starting large motors, the problem exists of limiting current through the rotor windings until a CEMF can be built up. If the full current is applied before the CEMF develops, it may burn out the rotor windings. Starting boxes are used with DC motors in order to avoid this application of current before the CEMF is built up. Here is a basic shunt motor with its starting box. In the starting position, the circuit to the rotor windings is closed through a series of large resistance coils. As the lever of the switch is moved, rotor speed and CEMF build up gradually, and the resistance coils are subsequently cut out until running speed has been reached. The lever is held in the fully open position by an electromagnet. If for any reason the power should fail or the field coil open, the electromagnet becomes de-energized and the lever is returned to the starting position by spring action. Just as in DC generators, DC motors seldom use permanent magnets for the field. Instead, electromagnets are used. Like with a DC generator, field windings are constructed in several ways. Each type of winding has special characteristics, special values, and specific uses. The series wound motor has good starting torque or turning force. Torque depends on armature current and on field strength. Since field strength is proportional to current, the high starting current before CEMF is developed affects torque as the square of the current. The motor begins to turn, attempting to develop enough CEMF to completely oppose the applied EMF. The load prevents this, acting to control the speed of the motor. But if the load is suddenly removed, like in the case of a broken belt, the motor will build up speed trying to develop more CEMF until it destroys itself. The shunt wound motor has less starting torque, but it is less dependent on load for speed control. In the shunt wound motor, the field coils are connected in parallel directly across the DC input terminals. The starting torque is not as great as in the series motor since field strength is not affected by armature current. The speed of a shunt motor is fairly constant under conditions of changing load. As more load is applied, the speed of the armature decreases. This decreases the CEMF and increases the current input. The increase in current input boosts the coupling between the field and armature and increases the torque, causing the motor to resume approximate running speed. A sudden reduction in load will not damage the motor because the field current is independent of rotor current in the shunt wound motor. The desirable characteristics of both the series and shunt wound motors can be achieved in the compound wound motor. In order to obtain good starting torque, the series field is used. When running speed has been attained, a centrifugal switch cuts out the series field and cuts in the shunt field. It is now a shunt motor and the speed regulation is good. Compounding provides good starting torque and good speed regulation. This allows for efficient operation and minimizes the possibility of damage to the motor. Now for a quick summary. The operation of all rotating electrical machinery is based on one simple principle: the generation of an EMF. The principle is used in the construction of a simple AC generator. The generator output E, or instantaneous EMF, equals B, strength of field, times L, length of the conductor, times V, velocity of the conductor. But because the movement of the conductor in the field is actually circular, we must also multiply with a sine of the angle formed by the lines of force and motion of the conductor in order to arrive at the EMF. All generators are basically alternating current generators and produce AC internally. The basic AC generator becomes a DC generator when a commutator is attached to the conductor. Each commutator segment rotates with its respective conductor, producing a direct current. This current, which is a pulsating current, is made smoother by the addition of more magnets and more loops. Sparking in a generator is sometimes caused by a shift in the neutral plane. This can be corrected by adjusting the brush position. Or by the use of interpoles and compensating windings. Current for field windings may be supplied from an outside source, in which case the generator will be separately excited. Or the current may be a part of the generator's own output, in which event it is called self-excited. Generator field windings are constructed in three ways. Series wound, where the field windings and the armature are in series. Shunt wound, in which the field winding is in parallel with the armature and the load. And compound wound, in which the best features of both the shunt and series wound generators are combined. Voltage regulation in the series wound generator is poor. In the shunt wound generator, voltage regulation is fairly good, but current regulation is poor. Compound wound generators provide stable voltage under changing loads. This output is normally most desirable. Motor action is the opposite of generator procedure. In a DC motor, voltage is applied to two or more loops in a magnetic field. This causes polarity in the loops. The interaction of this polarity with the polarity of the field makes the loops rotate. This is the basic DC motor. When the conductor of the motor is rotated by an applied EMF, it also generates a counter-electromotive force. According to Lenz's law, this generated CEMF must oppose the applied EMF. As in generators, field windings in DC motors are of three types. The series wound motor has good starting torque, but since its only governing factor is the load, the speed regulation is poor. If the load is disengaged suddenly, the motor will race to destruction. In shunt wound motors, with the field coils connected in parallel across the DC input terminals, the starting torque is not too good, but since the field current is independent of the rotor current, the speed regulation is quite good. The compound wound motor combines the best features of both types. It uses a series section for good starting torque. Then it switches to a shunt arrangement for good speed regulation. DC electrical motors and generators are at the heart of much military equipment. A proper understanding of them is therefore important.